much. Can people hear me? Yes? All right. A little bit louder, because I'm not sure I can amplify myself and write at the same time. Let's see. Is that better? Okay. So what I'd like to do is I'd like to tell you why the algebraic geometry of surfaces and the classification of surfaces is something that every arithmetic geometer should want to know about. Essentially, the reason why is that there are lots of examples of surfaces where when you write them down concretely in terms of equations, they look very different, but they're really the same. They're really birational or biregularly isomorphic, and without a little bit of theory, it's hard to tell whether they're the same. You don't want to prove the same theorem over and over again for different birational models of the same surface. So what I'd like to do in the first 2 or 3 lectures is to describe systematically how you decide whether 2 rational surfaces are isomorphic or birational over a given field, and how you can write down all rational surfaces as blowups of some special types of rational surfaces that are easy to analyze. So to this end, I'm going to focus today on rational surfaces over algebraically closed fields. And here I'm going to assume that the ground field is of characteristic 0. My main reason is just to avoid some technicalities that I don't want to worry about here. I don't want to have to deal with heckling about inseparable morphisms. So characteristic 0. So let me start with a classical example of cubic surfaces. Most of what I'm going to say actually was not done in Göttingen. I think it was done by Cayley in the other area controlled by the Hanoverians in England. There may be a few connections to Göttingen, but most of what I'm going to talk about is English and Italian mathematics. So I'll apologize to Yuri about that. He's not here, so I guess I don't have to apologize. Okay. So let me first of all explain what I mean. So by a cubic surface, I mean a smooth cubic hypersurface. And I want to give a construction that produces these. So here's a classical construction. So for some special cubic surfaces. So let me start out. Let's say we're given points P1 through P6 in the plane in general position. Let me explain what I mean by that. So let's see, how do the combinatorics of this work? I guess if I send this, I may not get that back. All right. So this means that the PI are distinct. No 3 are collinear. And all 6 are not aniconic. So I have these points. Now, what I'd like to do is I'd like to construct a rational map using these points. So let's consider the space these are the homogeneous cubics vanishing. At these points. And an exercise for you if you choose to accept it, is that this is a four-dimensional space. Another way of saying this is that the 6 points impose independent conditions on a 10-dimensional space of all cubic forms in 3 variables. The other fact is that the base locus of this linear series has a base locus just equal to those 6 points. Another way of saying this is that there are no random points in the plane where these cubic polynomials are simultaneously 0. So one way to produce a cubic polynomial that vanishes at all these points is you can just take lines like this. This is an example of a cubic polynomial vanishing at 6 points. You just take the linear equations satisfied by line joining pairs of the points. This is a concrete example. So what I'd like to talk about is we get a rational map from P2 into P3, taking a point to the value of these forms, which is well defined away from our points, P1 through P6. Now, how do we make this map well defined? How do we eliminate the points where we have indeterminacy? Well, what I like to do is I like to consider the blow-up map. Beta from X to P2. So this is just the blow-up at our 6 points. So the way to think about X is that where before I had a point, now I have P1s. And I'm going to denote these P1s by E1, E2, E3, all the way up to E6. So we have these exceptional. Now, here's the basic fact. So after blowing up, we obtain a morphism. So J from X into P3, so that if I compose beta with the rational map, let me call this rho, this is just equal to J. I've resolved the indeterminacy of the map by eliminating the base points. And this morphism is an embedding. X in P3. So when you have a linear series and you have base points, when you blow up the base locus, you get a morphism into projective, from the blown up variety into projective space. Analyzing the geometry of this gives me an excuse to develop some nice and useful notation. So how do we how do we analyze the geometry of J of x? Well, the key ingredient is the Picard group. Let me just remind you the relationship between the Picard group of a blow-up with the Picard group of the original variety. So we have that this is an orthogonal direct sum of rank 1 lattices corresponding to each of the exceptional divisors. Along with the Picard group of the thing that we blew up. So here we have that the self-intersections of each of these factors is equal to -1. So this is fairly standard notation. I'm going to let L denote the pullback of the hyperplane. From P2. So this is disjoint from each of the exceptional divisors. So the key observation here is that since our map is given by the cubics vanishing at the 6 points, I can describe exactly what happens to the polarizing class under the pullback by the morphism J. So here's the key formula. So if I take the pullback, this is equal to 3L minus E1 minus E2 minus E3 minus E4 minus E5 all the way up to E6. This just reflects the fact that I'm taking cubics with base points. At the P1 through P6. So in particular, the degree of the image well, the Picard group always comes with an intersection form. And so here I mean the orthogonal direct sum with respect to the intersection form. Since this is the intersection form, I can compute the image of the map by using simple intersection theory. So this is we take this divisor, we get 9 minus 6 equals 3. So in particular, we find that this is a cubic surface. And in fact, under our genericity hypotheses, it's even a smooth cubic surface. So this is probably something that everyone has seen in a course on surfaces or even an undergraduate course in algebraic geometry. And my only excuse for doing this is it allows me to set up the notation that we'll be using a lot in this school. So I realize that many of you have probably seen this before. So let's see. Okay. So I guess I can pull this down. Let me do that. Okay. So here's the next fact that I want to emphasize. So what can we say about these exceptional curves? E1 through E6? Well, let me just do the computation first. If I take E1 through E6, and think of them as sitting in J of x, sitting in P3, the degree of each of these curves is easy to compute using our computation of the hyperplane class. So this is equal to 1. In other words, these are lines in the cubic surface. And so the proposition is that the following 27 curves are all lines in X. So you need to know all 27 lines on the cubic surface. I'll be remiss if I don't mention them. And so you make sure I get all 27, because I might miss some. So we have the exceptional curves. E1 through E6. We have the proper transforms of lines through 2 points. And then I have proper transforms of conics through 5 points. And hopefully I have 27 altogether. So let's just recap what we've done here. Using this blow-up realization or the linear series description of how do you realize P2 blown up at 6 points in projective space, we've produced a whole bunch of cubic surfaces, smooth cubic surfaces, with 27 lines. And in fact, these 27 lines have lots of good properties that we can read off from the intersection properties of the lattice. So you could tell me how many pairs of lines, disjoint lines, you have in the cubic surface. If I have 2 disjoint lines, how many lines meet both of them? These are all questions that you can answer very explicitly from this explicit description. All right, this is all well and good, but we need to step back a little bit from this nice classical geometry and ask what we can say about general cubic surfaces. I mean, as things stand now, we don't know that all the cubic surfaces can be placed in this form. This gives us a whole bunch of cubic surfaces, but why is this all of them? So here are the questions that I like to turn to. And in some sense, these are a microcosm for all of the classification questions that we'll see for surfaces. So here are the questions I'd like to address. The first question is, does every cubic surface arise in this way? That is, are they all blow-ups of P2 in 6 points? And secondly, are there exactly 27 lines? So let me address this. Well, before I address it, let me make a definition. And this will give me a chance to introduce some more notation. So let's let Y be an arbitrary smooth projective surface. And let's let K of Y be the canonical divisor. So this is associated to the locally free sheaf, the top exterior power of the differentials. So we say that y is del pezzo if minus ky is ample. If some large power of the anti-canonical bundle embeds the variety into projective space. And one consequence of being del pezzo is that ky squared is always positive. Because if you take an ample divisor, you square it, you have to get a positive number. Or minus an ample divisor. So using this idea, we can start to analyze the structure of general cubic surfaces, ones that don't come a priori from this blow-up realization. Now I think I do need to try to I'm going to make a series of remarks about general cubic surfaces. By a cubic surface, I always mean a smooth cubic surface. I don't want to look at singularities in this lecture. So, so the first remark I want to make is that if I look at x in P3, this is cubic surface. We have by adjunction that k of x is equal to k of P3 plus x restricted to x, which is just equal to minus 4 times a hyperplane class. Which is minus a hyperplane class restricted to x. So this is a del pezzo surface. Now, one thing I should mention about del pezzo surfaces is that, well, we just saw there's all these nice curves. They have self-intersection minus 1. And these are so useful that we're going to abstract this definition so it can be used in general contexts. So if y is a smooth projective surface, so a minus 1 curve is a smooth rational curve E and Y with E squared equals minus 1. So I need here rational. There can be elliptic curves with E squared equals minus 1. So the rational is an important part of the hypothesis. And so an easy proposition, by the way, almost every proposition here is really an exercise. I mean, at this stage, the stuff I'm doing is something that you can, most of it you can address with bare hands yourselves. And so I'd be very happy if over lunch or over dinner you buttonhole me or other aficionados how to actually prove these yourself. Most of these are not difficult, but I have very limited time. So let's say we, again, have y as smooth projective surface, and let's say we're given E and y just irreducible. So that the canonical class with E is negative. and e squared is negative. So then e is a minus 1 curve. And in fact, this is probably the better way to think about minus 1 curves. It's important to see that they have the property that the canonical class is negative along them, and they have negative self-intersection. This is probably the right way to define them, at least from a functional standpoint. Okay, so I think, let's see. Uh-oh. All right. So the next remark I want to make is how do we classify them? The minus 1 curves on the K3 surface. So this is remark 2. So lines on the cubic surface are all minus 1 curves. The lines are exactly the minus 1 curves. Now, this is easy to see. This is just a computation with the adjunction formula. So well, you just use the adjunction formula. You can see that the lines are exactly the minus 1 curves. So then, let's write our line in terms of our basis. We get a whole bunch of numerical conditions on the minus 1 curves. So if we write L in this form, the condition L squared equals minus 1, it translates into a Diophantine condition. And the condition that Lk of x equals minus 1 translates into another Diophantine condition. And these are two equations in the integers. We can actually solve these equations using the techniques from quadratic forms. Or, I mean, if you're just good with completing the squares, that's probably the easiest way to see this. And the only solutions to these, I hope I didn't erase, are hidden behind that blackboard. I'm sorry. I don't think I can recover them. Let me try once. Hold on. Okay. That is probably unwise. They are there. Are hidden behind that blackboard. I'm sorry? Oh, that's a good idea. All right. Thanks, Amanda. All right. Wait a second. I erased them. All right. Oh, now you're making me look bad. All right. But anyway, the 27 solutions, I wrote them down. So the last fact I want to emphasize is so these are the 27 listed lines. So the last remark is that, so using these solutions, all cubic surfaces X, which arise as a blow-up of 6 points, have precisely 27 lines. But we don't know that all cubic surfaces have this form. So how do we extend this to an arbitrary cubic surface? Well, we need a theorem. So let's consider P19. So this is the space of all cubic polynomials in 4 variables. So this is a Hilbert scheme of all cubic hypersurfaces. And inside of here, we have the smooth cubics. So this is an open-end subset of P19. And we also have the incidence variety. Consisting of all pairs where X is a cubic surface and L and X is a line. And so this is sitting in P19 across the Grassmannian. And we have an induced map from Z restricted to U to U. This is the induced projection. All right, I need to state the punchline. So the punchline is that pi u is smooth of relative dimension 0. Now, what this implies as a corollary is that every cubic surface has 27 lines. With exactly the same intersection. Because the intersection numbers, they don't change in families. U is connected. So we have that every cubic surface has 27 lines. The fact that this is smooth means that every fiber of that map has 27 distinct points with no multiplicities. So you might expect in general that the lines on the cubic surface could acquire multiplicities where 2 or 3 lines come together. The key thing here is that that can't happen unless the cubic surface has singularities. So is there a question? Is there a question? No? Here's a sketch proof. Well, first of all, let me just point out that Z is proper. Because a cubic surface with a line can only specialize to a cubic surface with a line. The line can only become a line. Now, let's say that we, let's look at, given a line in the cubic surface, this is a normal bundle. Well, we know what this is. This is OP minus 1 because L squared is equal to minus 1. So we know what the normal bundle is. We also know that H0 is equal to H1. These are always equal to 0. Just using the fact that I know what the cohomology of this sheaf is. Well, this means that, so this is a tangent space. So essentially what we've just shown is that the space of all lines is always smooth and unobstructed of relative dimension 0. So this deformation theoretic argument shows us that the lines can never have multiplicities. They can never have non-trivial scheme structure. So this implies that the relative, so tangent space has dimension 0. So deformation theoretic arguments will come up a lot in the summer school, so we might as well start the first day. So now, having this information in hand, we can go back and we can classify all cubic surfaces. Remember our questions. Well, we've answered 2, right? We've shown that there are 27 lines on the cubic surface. And now we're going to use the fact that we understand all the minus 1 curves, we understand all the lines, to recover something about the geometry of X. So knowing that we have these lines, we can actually reconstruct all the geometry of our cubic surface. So there's lots of ways of doing this. So here's one way. So using the lines, we recover the geometry. So here, X is just a cubic surface. I'm not assuming anything else about it. So we know that we can choose lines, say E1 and E2 in X, which are disjoint. The intersection numbers don't change as I move in the family. So if I can produce 2 disjoint lines on one cubic surface, I can produce them on all cubic surfaces. And moreover, by the same argument, there exist 5 lines which are incident to both E1 and E2. So we have our disjoint lines. I have a whole mass of lines. Yeah.
How are we guaranteed two disjoint lines?
I know on the cubic surfaces that I produced by my blow-up construction, I have a whole mess of disjoint lines.
Right.
And if I take two of those lines, I can compute their intersection number. That intersection number is topological in the sense.
I recognize it on the blow-up version of things, but on the general cubes.
But the intersection number doesn't change as you move from one cubic surface to another. So once I can show that those lines actually move to all the cubic surfaces, anything that I compute about them topologically, it won't change from one place to another. So I'm making recourse to either a hard fact in intersection theory or an easy fact in topology, depending on your taste. And so what I'd like to do is I'd like to look at all of the planes containing E2. So, and look at the projections from P3 into P1. So these are the projection maps. So here's the theorem. Probably this only deserves to be a proposition, because I expect you to prove it yourself. So there exists a birational morphism from X to P1 cross P1, taking the point X to its projections under these You might claim that this is only a rational map, but its indeterminacy is a divisor, so there's really no indeterminacy. This contracts the lines L1 to L5 to points. If I were careful, I could tell you that these points are in general position in some sense, which I don't want to take the time to explain now. I can describe the inverse. The inverse corresponds to the type 2-2 forms vanishing at Q1 through Q5. Now, as a corollary to this fact, I get the following. All these cubic surfaces are blown up versions of P2. And I guess the key ingredient here is if I take a point and blow it up in P1 cross P1, this is isomorphic to the blow up of P2 at 2 points.
Sorry, what was this number?
This is 6 points. So we've recovered the fact that this proves that every cubic surface, is a blow-up of P2. So now, what I'd like to do is I'd like to abstract away from cubic surfaces and start to talk about general surfaces and how we classify them. There's a few morals that we should take from the analysis here. The main moral is that keep track of the -1 curves, because you're going to make your money with those. Understanding how they behave under birational morphisms is really the key to getting any traction when you classify surfaces. And I know that this is, quite an elementary case, but I think the point is that once we realized that the lines had a nice numerical characterization, and we could start working with them using that numerical characterization, the classification really fell out. So with this in mind, I want to move to a more general discussion of actually comes from blowing up. So this tells you why -1 curves are so crucial. They always come from blow-ups. So let me sketch why this is true. So this is a really crude sketch. If you want a honest proof, look at Beauville's book. We're going to actually, this is only the beta version of our contraction theorem, so I don't feel much moral duty to prove it. I'll feel more of a duty to prove the version 1.1. But let me at least sketch this to show you the idea. So let's say that H is ample. I'm sorry. Let's let L be ample on X. And let's let h be the divisor. Let me write it like this. Let's take the class of L. Let me use consistent notation. I apologize. Let's take h prime to be h, and I want to add h dot e, e. By the way you should think about this is I'm basically trying to automate projection and put it in an abstract form. So I'm going to have my lecture notes available on the web soon, and I'm going to give you lots of concrete examples where you can actually see these contractions in action in concrete situations. The thing that we should see about this is that if I take h and I intersect it with e, this is equal to 0, but hd is positive for each curve d not equal to 0. So we know that h meets every curve not positively. E meets every curve that's not e positively, because any two effective divisors with distinct supports intersect positively. So we have that this is positive. So this is almost ample in some sense. So the idea here is that we construct y to be proj over x so we use this divisor to construct. And whatever else happens, these sections are constant. Along E. So this definitely contracts the divisor E, whatever else it does. And that's all I'm going to really say about this. We'll come back to this in a little while. But this is a general contraction result. Now, once we have this, we have a pretty good control over all birational maps between smooth projective varieties. So let me show you how this works. So let's say we're given a birational morphism of projective varieties, projective surfaces. I guess I should say smooth. So then there exists a factorization where each term is a blow-up at points. So each one of these maps is a blow-up at a single point of xi. So every series of maps can be represented as a sequence of blow-ups. So how do we prove this? Well, let me show you how we can cook up the -1 curve. All right, for cubic surfaces, we know how to cook up -1 curves. I mean, we use this classical projective geometry. Now we need to be a little bit more clever in how we cook up -1 curves. So in some sense, cooking up minus 1 curves is the whole game here. And we're going to develop successively more sophisticated techniques to find them. So here's the idea. So what I'd like to do is I'd like to consider the map induced on 2 forms by pullback. So this is just the pullback on 2 forms. Now, these are both invertible sheaves. Because x and y are non-singular. These are rank 1 sheaves. But this is definitely not an isomorphism because we definitely have ramification. We have ramification where phi is not an isomorphism. But I know how to analyze a map of invertible sheaves. Right? I mean, it's going to be 0 on some divisors. That's the only thing that can happen. And so what I can do is if I let's let E1 to ER be all the curves along which, well, all the curves contracted by phi. That is, those along which phi is not an isomorphism, or along which we have ramification. Then I can write I hope I get the signs right here. I can write this as a sum where each one of these MJs is actually positive. The reasons why they have to be positive is if it's not positive, then the map is unramified along that curve. The map is unramified along that curve. It really can't contract it. I mean, it can't be contracted unless some derivative is vanishing. So I'm going to call these the phi exceptional curves. So let me write this in divisorial notation. K of x is equal to phi pullback K of y plus a sum mj ej. So this is sometimes called a discrepancy equation. This is the first if you've seen discrepancy equations in minimal model program talks, this is where they really come from. So now I need to use something. We have the Hodge index theorem. What that says is that, well, I have a whole boatload of positive divisors on y. Y is projective after all. So anything that's exceptional for the morphism has to be negative. So this implies that the intersection form is negative definite. So we have this negative definite intersection form on now. All right. I mean, we've seen these negative definite intersection forms before. When I blew up the 6 points on P1, I got -1, -1, -1, -1, -1. I'm just abstracting that away.